Consider the transmission of intelligence from one place to another. In this case, notes from a flute. The musical notes that we hear consist of a train of vibrations in the air. Falling on a microphone, they are converted into alternating electric currents. The resulting waveform can be plotted. The pitch of a sustained note corresponds to the fundamental frequency of the waveform. Raising of the pitch increases the frequency. The loudness of the note determines the amplitude of the waveform. The quality of the sound, which distinguishes notes of the same pitch played by different instruments, is determined by the number and the amplitude of the harmonics produced. That is, overtones at multiples of the fundamental frequency. We can plot the fundamental frequency and its harmonics in a different way. Here, the presence of a line indicates that a frequency is present. The length of the line shows its amplitude. More complex than simple musical notes, speech waveforms can be analyzed into a number of pure sine waves. The resulting spectrum becomes complicated and is, of course, varying all the time. In normal speech, most of the intelligence is at moderately low frequencies. Thus, whilst the whole speech signal occupies a fairly wide bandwidth, commercial telephone channels accept a band of frequencies only from 300 to 3,400 cycles per second. Within this frequency range, one pair of wires can accept only one speech channel. A second transmission made simultaneously would interfere with the first.
Hello, 15. Message for
Hello,
Proctor.
27.
Stores
Seagull
requested
speaking.
in your message
The conference
have been
at
dispatched to
Yellowstone
Crabtree.
is now cancelled.
Echo
In order to transmit two speech channels simultaneously, we must translate the whole of one channel up to another part of the frequency spectrum. This is done by impressing the characteristics of each speech wave upon a carrier wave in the part of the spectrum we wish to use. This is what is meant by modulation. By selecting a sufficiently high carrier frequency, we can transmit the signal by radio. For long-distance communication, the useful part of the radio frequency spectrum is very limited. This will influence our selection of a particular modulation process. To sum up, modulation is defined as the process by which the essential characteristics of a signal wave, the modulating wave, are impressed upon another wave, the carrier wave. Any sinusoidal wave, such as a speech waveform, has three characteristics: amplitude, frequency, and phase. Each of these characteristics may be used as the basis of a process of modulation. The vector is a convenient concept which enables us to learn more about amplitude, frequency, and phase. You see here a radius arm rotating about a point O. We halt it for a moment in this position and label it A for amplitude. Phi is the angular deflection of the arm from the horizontal. We see that Y is equal to A sine phi. Rotating the radius arm with a constant angular velocity, we see that although the arm is moving, the distance y is always equal to A sine phi. If we take the angular velocity as omega radians per second, then after t seconds, the angle phi is equal to omega t, and y becomes A sine omega t. Let us now plot a graph showing the variable distance y plotted against time t. If we start with the radius arm in the horizontal position, when t equals 0, omega t equals 0. Y is therefore also 0. And the waveform is the graph of A sine omega t. If, however, we start with the radius arm displaced from the horizontal by, say, an angle phi, then the graph starts with y equaling A sine phi and shows the function y equals A sine omega t plus phi. The amplitude is equal to the length A of the radius arm. The frequency is determined by the number of complete cycles per second, and phase is determined by the instant at which observation is started, in this case, angle phi. To duplicate this waveform exactly, we have to know all these three characteristics. To simplify the picture, let us eliminate the geometry and consider the radius arm alone. We will call it the carrier vector. Bear in mind that although it will frequently be shown still on the screen, it is in fact rotating at a constant frequency. Now, changes in amplitude can be expressed by increasing or decreasing the length of the vector. Changes in frequency by increasing or decreasing its angular velocity. And changes in phase by altering the angular position of the vector. Let us consider amplitude modulation. Here you see an unmodulated carrier wave with amplitude, frequency, and phase. And here, a modulating signal consisting of a pure sine wave. At the right of the screen, we place our carrier vector halted to show the amplitude of the unmodulated carrier. Now, on transmission, as the instantaneous value of the modulating signal rises from 0, the amplitude of the wave increases. We can express this also by increasing the length of the vector. As the modulating signal falls back to 0, the amplitude of the wave returns to its original value, and the vector to its original length. As the instantaneous value of the modulating signal becomes negative, the amplitude of the wave is reduced, and the length of the vector is reduced. You see that we are reproducing the modulating signal in the peaks of the transmitted wave, often called the envelope. How has this affected the carrier vector? We have seen that its length increases and decreases with the value of the modulating signal. We can express this geometrically by adding to it two new vectors representing different frequencies. They rotate in opposite directions. Thus, their resultant acts always along the line of the carrier vector. Again, you see how the variations in wave amplitude follow the modulating wave form. Thus, we can say that the transmitted signal is composed of three frequencies. The original carrier frequency, Fc, and two side frequencies. Carrier frequency plus modulating frequency, Fc plus Fm, and carrier frequency minus modulating frequency, Fc minus Fm. We can represent the picture more simply thus. Here you see the carrier and the two side frequencies, expressed in terms of amplitude and frequency. The side frequencies are equal to each other and are proportional to the modulating signal. There is, however, a practical limit to the amplitude of a modulating signal for any given unmodulated carrier. As the level of the modulating signal increases, a point is reached where the transmitted wave just disappears once during each cycle. At the peaks of the signal, the final modulated wave amplitude becomes twice that of the original carrier. In the same way, at the troughs of the signal, the final amplitude becomes zero. This condition is known as 100% modulation. For practical reasons, it's desirable to use rather less than 100% modulation to avoid the possibility of serious distortion caused by overmodulation. Also, there will usually be some noise. The modulation level must be sufficient for the signal to be detected through the noise. The signal amplitude range, which can be effectively transmitted, is from about 5% to about 95% of the carrier amplitude. Double sideband amplitude modulation has an important disadvantage. The amplitude of each side frequency must not exceed 1/2 of the carrier amplitude. Remembering that power is proportional to the square of voltage, this means that the intelligence is carried in two side frequencies whose combined power cannot amount to more than 1/3 of the transmitted power. Never less than 2/3 of the power is transmitted in the carrier itself, which itself contains no intelligence. This is a waste of power. Remember that in general we are interested not only in one audio frequency, producing a single pair of side frequencies, but in a whole range of tones. The peak sideband power can never be more than 1/3 of the total transmitted power, and will usually be very much less. We can represent the more complex sideband pattern accurately, or conventionally. Note that each sideband is a mirror image of the other. We can obtain all the information we want from a single sideband on its own. For instance, the amplitude of the modulating signal is proportional to that of either sideband. The frequency of any tone in the modulating signal is equal to the frequency difference between either of the corresponding side frequencies and the carrier frequency. Thus, if we can eliminate the carrier and one sideband, we can transmit all the intelligence required in the bandwidth of the remaining sideband. This is known as single sideband transmission. We may need to transmit the original carrier at a reduced level, or we may suppress the carrier altogether and generate a new carrier locally in the receiver. Here we have two double sideband signals, channel 1 and channel 2. Either of these signals can be transmitted independently. Channel 1 by eliminating the upper sideband and transmitting the lower, and channel 2 by eliminating the lower sideband and transmitting the upper. We find in practice that both channels can be transmitted simultaneously, using a common carrier frequency in one transmission over a single transmitter. This is known as independent sideband transmission, ISB for short. Let us start again with our carrier vector. Remember, its length A corresponds to carrier wave amplitude. Its angular velocity determines carrier frequency, and phase is represented by its displacement from a reference position. We have just considered a system of modulation in which the amplitude of the carrier varied. Now let us try keeping the amplitude constant, but swinging the vector about its mean position whilst it still rotates at an average angular velocity determined by the assigned carrier frequency. We can arrange for this change of phase to be made proportional to the amplitude of the modulating signal. Suppose we apply a square wave input to the phase modulator. At this moment, the vector is rotating with angular velocity omega. When the modulating signal becomes Vm, the phase advances to a value delta. This sudden change of phase is accompanied by a blip in the frequency graph. When the modulating signal becomes minus Vm, the phase is retarded by a value of 2 delta. Each sudden change of phase appears as a blip in the frequency graph. When the modulating signal becomes 0 again, the phase of the carrier has returned to normal. Instantaneous phase has varied, but average frequency has been maintained. The change of phase is proportional to the modulating voltage. If the modulating signal is sinusoidal, the instantaneous phase of the transmitted wave will follow the rise and fall of the modulating voltage. Again, the change of phase is proportional to the modulating voltage. Naturally, the number of swings in a second is the same as the frequency of the modulating signal. Let us examine the transmitted wave during a cycle or two of the modulating signal. When there is no modulation, we transmit a pure sine wave. As the modulating signal increases, the instantaneous phase of the transmitted wave changes. A positive modulating signal advances the carrier phase. A negative modulating signal retards it. Looking more closely at the transmitted wave during modulation, we see that although it looks superficially like a sinusoidal waveform, this is not so. Each cycle is slightly different from the one preceding it. Analysis of the system shows the presence of a number of side frequencies. The effect of phase modulation, as we have seen, is to produce a swing of the carrier vector. The amplitude of the swing depends on the amplitude of the modulating signal. The number of swings per second depends on the frequency of this signal. Again, let us illustrate this geometrically by adding side frequency vectors to the original carrier vector. In this case, we require a resultant which will not vary the length of the carrier vector, but which will create a swing about the vector's mean position by operating at right angles to it. Now, as the side frequency vectors rotate in opposite directions, their resultant causes the carrier vector to swing ahead of and behind its mean position as the modulating signal becomes positive or negative. Provided that the total angular deviation is small, the change in length or amplitude of the carrier vector is negligible. However, if the modulation index is increased, we can no longer say that the amplitude is not altered, and this error must be corrected. we must start with the carrier vector rather too short. Now, when we add the side frequency vectors, the resultant vector is too long. So we add 2 more side frequency vectors in the correct phase. Their resultant is vertically downwards, producing a new resultant vector of the right length. Note that the downward resultant of these 2 new vectors has to operate twice in each cycle of the modulating signal, once at each end of the swing, and that in the mid position, the resultant operates vertically upwards, extending the carrier vector to the right length. By means of the 2 pairs of side frequencies, we have now achieved a reasonable approximation to a vector of constant length, swinging through a fairly wide angle. The first pair corresponds to modulation frequency, and the second pair to double this frequency. That is, they are harmonics of each other. In fact, however great the angle through which we wish to phase modulate the carrier, we can achieve a satisfactory result by adding more and more side frequencies at higher and higher harmonic multiples of the modulating frequency. Now let us look at the side frequency spectrum obtained. When the modulation index is small, the pattern consists of a carrier and 2 side frequencies only, very similar to the amplitude modulation pattern. We must remember, however, that in phase modulation, the first side frequencies are in fact 90 degrees out of phase with those of the AM signal. As we increase the modulation index, more side frequencies will appear, each pair appearing 1 modulating frequency above and below the last, and the bandwidth occupied by the signal will increase accordingly. In phase modulation, we cause the phase of the carrier wave to alter, the change in phase being proportional to the amplitude of the modulating signal. Let us alter the carrier frequency itself. Now, the change in frequency must be proportional to the amplitude of the modulating signal. Suppose that we apply a square wave to the input of our frequency modulator. When there is no modulating voltage, the carrier remains at the assigned frequency. At this point, where the modulating signal is steady at Vm volts, the transmitted frequency has jumped to a new, slightly higher value, the change in frequency being proportional to Vm. Now the modulating signal falls to minus Vm volts. The transmitted frequency falls to a new value, lower than the original frequency, again by an amount proportional to the new modulating voltage. When the modulating voltage returns to 0, the carrier returns to its original frequency. If the modulating signal is sinusoidal, the change of transmitted frequency is also sinusoidal. The instantaneous value of the transmitted frequency at a given moment differs from the normal or rest frequency by a deviation proportional to the instantaneous value of the modulating signal voltage. Naturally, if the frequency of the modulating signal increases, the transmitted frequency swings more often between its lowest and highest values. We have thus transmitted both the amplitude and the frequency of the modulating signal without varying the carrier amplitude. We can look at this in another way, by plotting the instantaneous frequency when no modulating frequency is present. The instantaneous frequency equals the carrier frequency. As the value of the modulating signal rises, the instantaneous frequency rises with it. As the signal falls, the instantaneous frequency passes back through the original carrier frequency to a minimum value on the other side. Delta is the maximum instantaneous deviation of the carrier frequency corresponding to the peaks of the modulating signal. We must restrict our total bandwidth to that allotted to us in the frequency spectrum. Here, for instance, is the bandwidth allotted. We must decide the maximum allowable instantaneous frequency deviation, delta F. In a typical case, it may be plus or minus 15 kilocycles per second. The modulator of the transmitter must be arranged so that the instantaneous frequency transmitted does not exceed these limits. Remember how in phase modulation the number of side frequencies went up as the modulation index increased. Well, now in wideband frequency modulation, a very large number of side frequencies may be present, and the modulation index can be very large indeed. Notice how the amplitude of the carrier frequency component shrinks as the modulation index rises. When M reaches 2.4, the carrier frequency disappears altogether, and we're left with a complex pattern of side frequencies. As we further increase the modulation index, still more side frequencies appear. The carrier reappears, and the whole process is repeated cyclically as we increase the modulation index to a very high value. Consider now the effect of noise on the frequency modulated signal represented by this vector. It is, of course, rotating at an average angular velocity determined by the carrier frequency. And superimposed on this rotation are wide variations of average velocity due to frequency modulation. Noise will exist as a more or less continuous spectrum of radiation throughout the bandwidth. Here you see a vector representing a noise signal at about carrier frequency. This, of course, is also rotating, and at a given instant it produces a resultant. At this instant, the resultant is longer than the carrier vector. That is, an amplitude-modulated component has appeared. Furthermore, as the noise vector rotates, the resultant swings about the mean position of the carrier vector through an angle which we will call psi. Since in our receiver we are at present concerned only with frequency, we can remove the entire amplitude variation effect by means of a limiter circuit, cutting off the peaks of the signal. The resultant vector is now constant in amplitude. There is, however, a variation in phase, represented by psi. But angle psi can never be more than pi radians, whereas the change of phase due to frequency modulation may be many complete revolutions of the FM vector. A very large angle indeed. Thus, psi represents a very small proportion of the total angular displacement and will have only a very small effect on the receiver output. In fact, frequency modulation has a built-in resistance to ordinary atmospheric noise. And with a frequency modulated signal of reasonable amplitude, noise levels, including unwanted signals even fairly close to the level of the wanted signal, are almost entirely eliminated. Why don't we use FM for everything? Well, the answer is that in the short and medium wave bands, there is simply not enough spectrum space for wideband frequency modulated transmissions. However, for applications where range is not all important, the frequency can be put up into the VHF band or even higher. Finally, let us compare frequency and phase modulation. Here you see a modulating signal. For clearness, we show it as a square waveform rather than a sinusoidal one. Above it, you see the waveform of the corresponding frequency modulated signal. Below, you see the corresponding phase modulated signal. Up to this point, there is no modulating signal, and both transmitters are radiating at a carrier frequency, FC. When, however, the modulating signal suddenly rises, the two transmitters behave differently. The frequency modulated transmitter sends out a signal at an altogether new and higher frequency, FC plus delta, whereas the phase modulated transmitter appears to continue at frequency FC. A close inspection, however, shows a break in the signal continuity. The phase of the signal has been advanced by an angle phi proportional to Vm. Similarly, at the instant where the modulating signal level falls, the FM carrier frequency falls to below its original value, whereas the PM signal carries on at frequency FC, with another discontinuity, the phase being retarded by an angle 2 phi, and so on. In practice, the modulating wave cannot be truly square, and the change of phase will be rather less abrupt. Although phase and frequency modulation are obviously similar, there is an important difference. Remember how our vector was derived. The unmodulated carrier corresponds to a sine wave whose equation is little vc equals vc sine omega ct plus phi, where phi is the phase. The modulating waveform is also sinusoidal. Suppose that its equation is little vm equals Vm cos omega mt. In phase modulation, we make the phase of the carrier equal to some constant k times the instantaneous value of the modulating signal voltage. Little v phase mod equals Vc sine omega ct plus k times Vm cos omega mt. The term k times Vm is the modulation index for phase modulation. It's proportional to the amplitude of the modulating signal and is independent of its frequency. That is, if the level of the modulating signal is held constant at, say, 1 volt, and the frequency is varied, the modulation index will remain unchanged. In frequency modulation, the effect of modulation is to speed up or slow down the rotating carrier vector by an amount equal to the instantaneous modulating voltage. That is, the phase is being continuously changed. Considering the square waveform modulating signal for a moment, at the beginning of the first half cycle, the phase of the phase-modulated carrier jumps to a new value, phi, and remains there steady until the modulating signal changes. Obviously, here it's the change of phase which is important, and which carries the intelligence. In the frequency-modulated case, the vector rotates faster. That is, the phase continues to increase until the modulating signal changes back again. Here it is the rate of change of phase which is important. This rate of change of phase will depend upon the frequency of the modulating signal as well as on its amplitude. And we find that we can express the equation of the frequency-modulated carrier thus: little v fm equals vc sine omega ct plus 2 pi delta over omega m sine omega mt. Here, delta is the maximum deviation of the instantaneous frequency from the average and is proportional to the amplitude of the modulating signal. However, the modulation index must now be 2 pi delta over omega m, or k dash vm over omega m. Comparing the modulation indices for phase and frequency modulation, we see that in phase modulation, the modulation index depends only upon the amplitude of the modulating signal, whilst in frequency modulation, the modulation index, although still proportional to the amplitude, is inversely proportional to the frequency of the modulating signal. That is, for two modulating signals of equal amplitude, but of different frequencies, the signal with the higher frequency will produce a lower modulation index than the signal of lower frequency. Each system of modulation that we have seen has its particular advantages and disadvantages. Any improvement in quality, in signal-to-noise ratio, or in more efficient use of power must be paid for in complexity and expense of equipment, or in increased bandwidth.